So we're going to go through quickly now some questions, more optimization problems. And the first one we're going to do is number 6. So what are the dimensions of a rectangle with an area of 64 meters squared, so that's going to be the constraint, and the smallest possible perimeter, so that's what we want to minimize, the perimeter. Okay, so the area is 64 and we want to minimize the perimeter. Okay, so this is a rectangle. So here we go, here's a solution for this. So the area is 64, so we've got that. Area equals x times y. Okay, so x is going to be 64 over y. The perimeter is 2x plus 2y. Okay, so this is fairly straightforward so far. You know the perimeter formula, and we're going to substitute in the expression for x here, which is 64 over y. So now we have the perimeter in terms of just y, which is like this. Or we can get it into this rational function here. But I'm going to take the derivative of this one. So take the derivative, we get negative 128 over y squared plus 2. Set that equal to 0, and we're solving this part right here. Okay, so negative 128 over y squared plus 2 equals 0. Rearrange that, you get y squared equals 64, and therefore mathematically that gives you y equals plus or minus 8. We're only choosing the positive 8 because we're doing positive dimensions for this rectangle. We don't have negative dimensions. Sub that in for our formula for x up here. Okay, so x equals 64 over y. 64 over 8 gives us 8 for the other one, and we have a square. Okay. Graphically, this function here, this function right here, would look something like this one. And so negative 8 would give you a local maximum, whereas positive 8 gave you a local minimum. Okay, so that's number 6. Number 9, let's take a look at this one. In number 9, you're given the volume of a prism, and it's square-based, and you're also given that the dimensions cannot be less than 2. Okay, so the volume is 1,000, so that is the constraint, and you're looking at minimizing the surface area. So say maybe it's packaging for some sort of like a box of cereal or something like that. Okay, so the volume is x squared y. The surface area is 2x squared, so the top and the bottom, plus 4xy, so 4 sides. And the easiest one to solve for here is y because it's only in one place in this formula. So you're going to solve for y, not x squared. Substitute it in, simplify, take the derivative, set it to 0, solve for x, that minimizes that surface area, and sub it back in to y to get the other dimension. And then we have the dimensions are going to be 10 by 10. It's going to be a cube. Okay, so not surprising based on some math that you've seen before. This next one is number 10. So number 10, right here, it is, okay, the volume of a sorry, it's number 10, which is that one. Determine the area of the largest rectangle that can be inscribed inside a semicircle with a radius of 10. Place the length of the rectangle along the diameter. Okay, so here's a diagram inscribing a rectangle inside a semicircle where the length is along the diameter. We know that the radius is 10, so the diameter is 20. Okay, we can figure out a constraint here because we know that the area for this is going to be length times width, and we can't have two variables in there, we need one. So from this we can use Pythagorean theorem to relate L to W. If this is the length of the rectangle, then that's L over 2. And then there's the width. Okay, so we know that 10 squared equals L over 2 squared plus W squared. Okay, so that's our constraint right there. And from that, we get L squared over 4 plus W squared equals 100. And we can keep working that down until we get a formula for L, which is 2 times root 100 minus W squared. Subbing that in into the length times width formula gets us this. Area equals length times width. Area equals 2 times the square root piece times W. Now we've got just one variable. Okay, now we're going to take the derivative. So the derivative of this is a product rule. Derivative of the first is 2 times the second plus 2W times the derivative of the second, which is the chain rule. You bring the 1/2 down inside, reduce it by a power, or by 1, then times the derivative of the inside, which is negative 2W. Once you've done that, you can rewrite it as these. Okay? And at this point, now you can solve the numerator to see when the numerator equals 0. Well, you're going to want to reduce that a little bit, so simplify it. Okay? So simplifying the numerator gives us this. And at this point, you get W squared equals 50, square root 50 equals 7.07. But if we sub that back in, exact values, we can get the length. Okay, and then it's looking for the area. So we're then going to multiply those two to get the area, which is 100 square units. And that's it for that problem. Okay. Number 11. Number 11 is an interesting problem. Okay, so you've got a cylinder with a certain capacity. That's going to be the constraint because it's given. So determine the dimensions that require a minimum amount of tin for the can. Okay, so you got the can is going to be shaped like this. The radius is given. You know that the volume is given. Volume equals pi r squared h, which equals 1,000. So there's the constraint. They give you information that r has to be greater than 3 and h has to be greater than or equal to 4. So I'm solving for h in this one because the surface area for this, well, if you unwrap that can, you get this net. So this side here is 2 pi r because it's the circumference of the circle, and here's h. And then you've got 2 pi r squareds. So the area of this is 2 pi r times h. Okay, so 2 pi r times h plus 2 pi r squared. At this point, I did something that I didn't like, obviously. I started factoring out the common factor. Didn't really need to, so I'm just subbing in what I saw for h here, and I'm plugging it in here. The pi's cancel out, the r's, and you get 2,000 over r plus 2 pi r squared. Now, standard thing here is to take the derivative, set it to 0, solve for the dimensions. Okay? That's number 11. Number 12. Number 12 is interesting. You've got a couple ways of doing this. You've got to inscribe a rectangle of maximum area where the height of the rectangle is 12 and the base of the rectangle is 5. It's a right triangle. Okay, so a right triangle. If we decide to let the base of the rectangle be x and the height of the rectangle be y, then we know the base of the triangle is 5 and the height of the triangle is 12. Then this piece is 5 minus x, and that's going to be 12 minus y. So the first way I'm going to set up this constraint is through equations of lines. If we let this be an x-axis and a y-axis, then we can say that this point here is a point on this line. So the equation of that line, well, the slope is going to be rise, which is negative 12, the run, which is 5. The slope is negative 12 over 5. The y-intercept is 12. okay? So slope, y-intercept, plug it in. Now that relates the x and the y. So there's the constraint. Or we can take these two triangles, realize that they're similar triangles. That angle is the same as that angle. These are both 90 degrees. This angle is the same as this angle. So they're similar triangles. So side ratios are the same. The whole basis for trigonometry. So we know that for this one, y over 5 minus x is going to equal 12 minus y over x. Okay, this side to this side is this side to this side. So we write that down here. Y over 5 minus x equals 12 minus y over x. Rearrange it, simplify, and we end up with the exact same constraint. So the area of that rectangle is x times y. Too many variables. So we're going to write x times this expression for y. Now we take the derivative, set it to 0, and so on. Okay, so that's number 12 set up. Number 13. 13 is a fun one. 13 is a trough, and the question, it wasn't very clear that it's an open-ended trough. Okay, so there's no ends to this trough. So this is the question here, number 13. Okay. So an isosceles trapezoidal drainage gutter is to be made so that the angles at A and B in the cross section ABCD are each 120 degrees. So the metal is 5 meters long and 60 centimeters wide. Determine the dimensions that maximize the cross section, the trapezoidal cross section. Okay, so we want to maximize this ABCD section here. Okay. So to do that, we've got, we drew the trapezoid here. Okay, so 120 degrees. And we've got one constraint, x plus y plus x is going to be 60 centimeters. Okay, so 60 centimeters right there. And so 2x plus y equals 60 centimeters, so y equals 60 minus 2x. And the area of a trapezoid is a plus b, the average of those two, times the height. So a plus b divided by 2, the average of those two, times the height. Now we've got to break it down for our trapezoid. This angle here is 120. Take away 90, and we have 30. That makes a 30-60 triangle. Okay? From that, we get these nice equations here that relate x and h and x and w. Okay? So cos 30 equals h over x, so h equals root 3 over 2x, using our special triangles. And doing the same thing here, we get w equals x over 2. And b, which is the top side of this trapezoid, the whole thing, is y plus 2w. 60 minus 2x is y, which we figured out up here. And then plus 2w, and we get b is 60 minus x. Now we've got this formula. Area equals the bottom plus the top divided by 2 times the height. Work that all out, we get this nice equation here. It's a quadratic. Take the derivative, set it to 0, and we get x equal to 20, and now you can find the other dimensions.